Hi, everyone. I'm Michael Woolley. I recently read An Imaginary Tale, The Story of the Square Root of Negative 1 by Paul Nahin. And so today I will be giving you a brief history of the square root of negative 1 as told in this book. Now let's start in the beginning. So, what was the first example of the square root of negative 1? You're probably wondering. Well, historians believe that Heron of Alexandria is likely the first person to have stumbled upon it, and he stumbled upon it during his work with frustums of pyramids, specifically square based pyramids. Now, one of the things Heron found was how to calculate the height of a frustum of a square based pyramid given only the length of the lower base, upper base, and slant. Now, once he found this, he considered a frustum with a lower base length of 28, an upper base length of 4, and a slant length of 15. But when he plugged this into his formula, you can see at the end he gets the square root of 81 minus 144. Now, obviously, that is the square root of negative 63, but what did Heron write down? Well, it appears that he wrote down the square root of 63. Ah, so close! Now, historians believe that he was aware that it was the square root of negative 63, but he just pretended that he did not see that. But let's cut him some slack and consider just how abstract the square root of negative 1 was. Well, to give some context, let's consider the negative numbers. Now, for centuries, ancient mathematicians just avoided negative numbers altogether. If they wrote algebraic equations, they always made sure to have positive coefficients, and if they were trying to solve algebraic equations, they would just simply ignore negative roots. And even as recent as the 16th century, mathematicians referred to negative roots as fictitious. And the main mental hurdle here is since 0 is nothing, right? How can something be less than nothing? Because negatives are less than 0. How can you have something less than nothing? That's just incomprehensible. And a perfect example of this confusion can be seen in John Wallis's statement, a famous mathematician during the 17th century. He said, since a divided by 0 with a greater than 0 is positive infinity, I don't know if I agree with that, and since a divided by b with b less than 0 is a negative number, then this negative number must be greater than positive infinity because the denominator in the second case is less than the denominator in the first case. So, as you can see, negative numbers, very abstract. The square root of negative numbers had to be completely mind-boggling. But you're probably wondering now, well, what was the first progress made towards understanding the square root of negative 1? Well, let's take a look at Girolamo Cardano, or Cardan, of a 16th century Italian mathematician. He proposed a problem of dividing 10 into two parts whose product is 40. Seems simple enough. So his solution was to let the two parts of 10 be x and 10 minus x. Therefore, multiplying these together, x times 10 minus x equals 40. That can be expanded to x squared minus 10x plus 40 equals 0. Now, we can solve quadratics, which he found the root to be 5 plus the square root of negative 15 and 5 minus the square root of negative 15. Now, most mathematicians of this time would have just stopped here and said, well, it was fun while it lasted. We do not have a real root. But Cardano decided let's take this a step further. Now, if we add these together, of course, the square root of negative 15s cancel out, and you're just left with 10. So that part works. And then he decided, let's try to multiply these together. And as you can see, after doing all the algebra, we get 40. So what Cardano concluded was that you can manipulate the square root of negative 15 as long as you put aside the mental torture involved. Speaking of mental tortures, Cardano actually discovered how to transform any cubic into a depressed cubic of the form x cubed equals px plus q. And he could solve this using the Cardan formula. And he soon realized that this formula could result in squaring negative numbers even when all the solutions were real. For example, he considered x cubed equals 15x plus 4. Now, if you plug this into the Cardan formula, you could see we get the cubed root of 2 plus the square root of negative 121 plus the cubed root of 2 minus the square root of negative 121. Now, this left Cardano completely confused. He had no idea where to go from here. But no need to fear. Raphael Bombelli comes to the rescue. He was a follower of Cardano, and he used this crazy manipulation and substitution of variables to figure out that these terms actually simplify to 2 plus the square root of negative 1 and 2 minus the square root of negative 1. So when you add these together, you get 4, which was one of our roots. And once Bombelli was able to demonstrate how the square root of negative 1 follows the rules of arithmetic, then it legitimized its usage for many other mathematicians. But once mathematicians have rationalized the use of the square root of negative 1, then they wanted to be able to geometrically construct it, and they tried to do this for the next 300 years. But it wasn't until a non-professional mathematician, Caspar Wessel, in the 18th century, came along and figured it out. Now, by this time, the geometric representation of negative numbers was generally agreed upon to be the length of a line segment measured to the left of some origin point. This may seem irrelevant now, but it will be important later, particularly in Wessel's 1799 paper. Now, Wessel understood that complex numbers have, of course, a real and imaginary part, and he realized that this could be represented on a plane, in fact, the complex plane, where the imaginary part is one axis and the real part is another axis. Building off of this idea, he then realized that complex numbers could be expressed as a distance from the origin, the radius vector, and the angle measured counterclockwise from the real axis, called the polar angle. Now, after discovering this, he then proceeded to invent vector addition and vector multiplication. But it was his vector multiplication that actually yielded the first geometric representation of the square root of negative 1. So, how did he define vector multiplication? Well, he said you simply multiply the lengths and add the angles. So, let's let the square root of negative 1 equal some length and some angle theta. And squaring both sides obviously gives us this negative 1 equals our length squared at angle 2 theta. Now, recall the geometric interpretation of negative numbers. It was the length measured to the left of some origin. Thus, we could write negative 1 as just 1 at the angle 180 degrees. Thus, we have our length squared at angle 2 theta equals 1 at angle 180. Thus, L squared must be 1, and 2 theta must be 180. Thus, L must be 1, and theta must be 90 degrees. And plugging these back into our original equation gives us the square root of negative 1 being 1 at 90 degrees. Now, what does this tell us? Well, it tells us that multiplying by the square root of negative 1 represents a 90-degree rotation counterclockwise in the complex plane. Now, while this is all extraordinarily fascinating, no one actually read Wessel's paper, unfortunately. In fact, no one even knew about it really until 100 years after he published it when it was rediscovered. But people did find out about all these when Gauss published a pretty identical paper 30 years later. And before you think he plagiarized it, there's actually evidence that he knew of all this years before Wessel even published his paper from his notes. And in fact, Gauss is actually the person who coined the term complex number. Nonetheless, it wouldn't be a history of the square root of negative 1 if we didn't include our main man, Leonhard Euler, Swiss mathematician of the 18th century and just super math genius. He was actually the first to use I to represent the square root of negative 1. Fun fact. But unlike most other mathematicians of his time, he didn't need to know the geometric representation of the square root of -1 before jumping in and discovering so many incredible properties of the square root of -1. In fact, one of these properties, published in his 1748 paper, over 50 years before Wessel, was that e to the ix is equal to cosine of x plus I times sine of x. Now, how exactly did Euler derive this? Well, he used his extensive knowledge of the power series expansion for e to the y, as you can see here, and substituting I times x gives us this. And when you separate the real and imaginary parts, you can substitute the power series expansions for cosine x and sine of x respectively, yielding e to the ix equals cosine x plus I times sine of x. But let's not stop there. Let's plug pi into this just to see what happens. Whoa, look at that. E to the I times pi plus 1 is equal to 0. Isn't that just the craziest thing you've ever seen? That is just incredible. Well, that concludes our brief history of the square root of -1. Of course, this just scratches the surface of its extensive history. We didn't even get into complex function theory. But if you want to learn more about it, I highly recommend reading Paul Nahin's book. It's an incredible read. But without further ado, until next time!